Hello everyone. In this 15-minute tutorial, I would like to show you how you can use OrthoSAM for a high-resolution orthomosaic. The orthomosaic we are going to use is from the northwestern Himalaya, from the Ravi River, and this is published data at the Zenodo link. And if you look at the Zenodo link, you see that we are providing 3 high-resolution images. They all have a spatial resolution of 0.2 millimeters, so these are fairly high resolution with roughly 20,000 by 20,000 pixels. These were generated with a Sony camera. Roughly 300 to 400 images were taken in order to create that compiled orthomosaic. The processing was done using Metashape, and you can tell that there are some artifacts in the data, including myself creating shadows when generating this data set. So we are going to use that Ravi 2 orthomosaic, and we are clipping out an area of 8,192 by 8,192 pixels, and we are doing that to have a more digestible data set. You can of course run the entire orthomosaic, but we are going to use that subset to make it a little faster in the processing chain. So please clip that area. You can use either ImageMagick or you can use any other software to create that clip. In the end, you have a new PNG file that is 8,192 times 8,192 pixels large. So we have that in the same directory where we have the original orthomosaic, and we are going to create the main parameter list. The parameter list control what OrthoSAM is doing with your file. The first thing that we said is what is the file that we are going to process? We are going to process the first file in that directory. It starts counting at 0. So the 0 would be that original the original file, and then the ID1 is that crop file. And we are setting the parameters of where to store the output data, and I'm going to store it in the Ravi output directory, and I'm adding the up5 because we are also using an upsampling of a factor 5. So this is why I'm adding up5 here. I'm going to explain this in a second. The data set name is stored in Ravi, and the file ID is ID1 that we just set. That is the crop that we are created. Because we are using a scaled image, we can set the resolution to 0.2 millimeters. OrthoSAM is tailored for high resolution images, so please make sure that you have the adequate scales in your mosaics when you generate them. We are going to use the tile size of 1024, and we are going to use an overlap of 200. Because we have a very high resolution image, we are going to do a resampling of 1/3. So, which means that we are taking the original 8,192 times 8,192 image, and we are reducing it by a factor of 3 in the X and in the Y direction. And we are doing this to speed up processing and because the pebbles that we are seeing are likely larger than the 0.2 millimeter resolution. We are going to look at 30 by 30 seed points per tile, and we have some additional filtering steps that we are not explaining in detail here. We are setting a minimum size of the smallest pebble size, that is 50 square millimeters. That's a fairly small size, and this can be adjusted if you are looking at larger pebbles. We are calculating the output statistics. We are ignoring the Discord notification that is mostly useful when you do very large scale processing of large orthomosaics that will send a message to your Discord account when you are done. And we are plotting the output. In the next list, we are defining the parameter list of the second run. So this is our first run, or layer 0, and this is our second run, layer 1. And in the layer 1, we are applying a resampling factor of 1/5. So we are resampling this, or we are upsampling by a factor of 5, because that is reducing the resolution even more. In a very common setting, you have the resampling factor of the first layer at 1, so that's the original resolution, and then you have a reduced resampling factor of 1/2 or 1/5, but that completely depends on your setting. We are using a resampling factor of 1/3 here, just to create an output in a much more rapid way. You also have additional pre-processing parameters, so you can apply a Gaussian filtering, you can apply local normalization using the Klahe filter, a histogram equalization, you can apply an additional resampling or some buffering. So the idea of this parameter list is that you can apply all of these steps to the same steps to a larger list of images. So the idea of generating this list here is that you can not only process a single image, but that you can process an entire directory of multiple images, and that can then run on its own. Here, once you have identified the parameters, we can verify them. These are the verification of the parameters. We can make sure that we are generating all the output directories. So that's usually good to check that all your paths are given in the proper way. And then we can do the first initial assessment, and that is to see where we have the tiles and where the tile overlap. So what I'm showing you here is a tile overlapping without the resampling. So this would be the tile overlapping on that 8192 times 8192 image. And this would be at the original resolution without resampling, and we would be generating quite a few tiles. So that would be very time consuming to process this at the full resolution, and therefore we are resampling this to 1/3, meaning instead of the larger number of tiles, we end up having a smaller number of tiles that will process much faster. The idea of OrthoSAM is that all the parameters are being stored in a JSON file. This JSON file then can be used to perform the processing. Very often you do the processing on the same computer where you generated that initial JSON file, but if you happen to have access to a fast GPU or a high performance cluster, you can just move the image, the JSON file and OrthoSAM to that cluster and then run it headless, so without a graphical user interface. All you would need to do is call or import OrthoSAM and call OrthoSAM with that parameter list. So all of the defined parameters then are running through, including the resampling, pre-processing steps, and post-processing steps. So I have done this for this example already, and I'm just going to talk you briefly through what the outputs are that you see. So we start with the processing, and we have the output of the first layer, or layer 0. And here we have that resampling step. So we are applying a resampling step to the 8192 times 8192 image. The size of that array is times 3 because we have the red, green, blue channel. We are tiling this into 16 tiles. We are processing it on the GPU. So I would like to stress the fact that you will need a GPU to do it in a reasonable amount of time. So you would need to have either a GPU access on your local hardware, or you have access to a remote system that allows you to run this. I have a separate video that explains how to use this on the Google Colab engine, but I'm stressing the point that the free version of Google Colab is not very efficient for working with large orthomosaics. So we are loading in that high resolution model from SAM, and then we are doing the segmenting for each tile. We have a total of 16 tiles. We are running through this for every tile. Every tile roughly takes 30 to 40 seconds. So that is something that will run through, and at the end of processing all 16 tiles and applying additional filters, you are merging the tiles. So OrthoSAM is merging the tiles and creating one coherent image. The details of this are described in the manuscript, but the merging is an integral part of making sure that no labels are counted twice and that you have an output data set that is coherent. The merging goes generally very quick, and you then see the first output. So the first output is your input RGB image, downsampled or resampled with a factor of 3. We have the following segments, and this then is a segment mask where each of the segments is separated out. What you can immediately see that a few pebbles are missing. So for example, this guy is missing here, and those two larger pebbles are missing here. And the reason for that is that they were larger than the individual tiles. So they could not be separated out because OrthoSAM is only including tiles or only including segments that are not touching the boundary. So that's the reason why these pebbles are being removed from the data set, because they are touching the boundary of the image. In order to get those larger pebbles and identify them, we are doing a second layer processing. This is now layer 1. You start at layer 0. This is layer 1. And layer 1 has an downsampling factor of 1/5. So we are applying a 1/5 downsampling factor, which further reduces the size, and you tile that image then eventually only into 4 tiles. That goes fairly quickly, the segmentation of those 4 tiles, and then again, a merging is happening, and the merging produces a new output image. So this is now the second run, and you see that those additional pebbles have been identified, but also many other pebbles that were already previously identified. The way the merging process of different layers works is that OrthoSAM is assuming that the first layer has priority, meaning that the layer that we generated up here is the highest resolution layer and therefore likely the most trustworthy outlines, and that the second layer only provides then the additional labels, which means that if we are going to merge those 2 layers, again, we have our RGB image. This is the results from the layer 0 or the first layer, and this is the result of the pebbles or the individual segments that are being added. And you're only adding the segments that are not already in the original data set. That then allows us to capture those larger pebbles. You see that there are some awkward pebbles in there that likely are artifacts because of overlapping pebbles and then seeing the pebble below. And this is something that we are going to remove in a separate filtering step. But you now have an output mask that can be used for further analysis. And what we told OrthoSAM to do, we told OrthoSAM to calculate the statistics, and the statistics are calculated for each segment separately. And this is what I would like to work with next. I'm calling this verify results and plotting. So I'm loading in that statistics file, and this is placed in the output directory, and it's called props.csv. This is the properties.csv. That's a file that can be easily read by pandas. So we are loading in that database into merge results, and we are looking at the first couple of data sets. So we see that we have the label. The label is our ID that is also included in our image. We have the centroid location, we have the major and the minor axis length, so this is A and B. We have the area, we have the perimeter of that segment, and then we have several metrics that allow us to measure the roundness of the pebble. This is a way to filter out pebbles, or to filter out segments and labels that are likely no pebbles. And we do have 6 columns describing the color distribution. So we have mean red, mean green, and mean blue, and median red, green, blue. And those information can be used in a, for example, random forest classification to do a segmentation of lithologies, or looking at other parameters related to color. I'm stressing the point that this is something that will be covered in a separate recording, because that will go beyond of what OrthoSAM is currently doing. We can obtain the averaged statistics of this. We see that there are some pebbles that have infinitive values because they are either too small or they have other artifacts, and we are going to remove them. So let's do the first plot of just plotting the centroid location. So we are using the centroid X, the centroid Y location, and we are plotting the color as the major length. This is the A-axis, and we are scaling the size by the area. So the larger the circle, the larger the pebble area, and the color indicates the axis length. So that's the first assessment of the identified pebbles. We can also load in our original image and superimpose the centroids on those on that original image. Note that we have to multiply the x and the y coordinates with 3 because we use the 3 a factor of 3 resampling. But that is a first order assessment, and it shows pretty well that the segments have been identified as we would have expected. So the ones that are touching the border are not identified, but also we identify the overlapping pebbles. So when this guy sits above this one, we have separated out both as segments, and likely this is something that we would like to avoid and filter out, and this is something that we are going to do in a couple of minutes. Let me just point out that you can also load the individual segments. So that props.csv file that I've been loading here is essentially a summarized statistics file. A CSV file, a fairly small file that can be used for visualization and analysis, but you could also load in the original segmented mask file that's stored as a NumPy array and can be loaded in and also visualized. So what we are doing here is that I'm loading in this as a array, and I'm converting the array to a floating point array because I would like to set the background to NaN. That makes the visualization a little easier. And then I'm showing all of the segments with a random color map, random grayscale color map, and superimposed on it the axis major length. So here we are seeing the segments and the centroids, and we can verify this with the RGB image, for example. So let's talk about filtering. We can filter out pebbles according to its roundness, and that is something that has been done in the past, and there is a large body of literature available that is looking at pebble shapes and pebble roundness factors. And I'm just pointing out some of them here that have provided quantitative assessments in the past. The term that we are using is the isoperimetric ratio, which is just the ratio of the area in 2D to the perimeter of the label. That's something that we can extract very easily from the mask. So our IR ratio is the the roundness factor, the isoperimetric ratio. That has been shown to be affected by the shape of that pebble. So if you have an elongated pebble, it may not represent a good IR. So that's why you have generated a normalized isoperimetric ratio, which is also something that we are providing in that table. We are going to use it IRN to visualize it. Again, if you would like to have more information about the pebble roundness metrics, please see those publications and or the main manuscript according to OrthoSAM. So we can load the image again and we can plot the IRN, the normalized isoperimetric ratio for each of the pebbles. And we see that most of the pebbles are, or most of the pebbles and boulders are around 0.8 to 1, which is what we would expect in a well-rounded environment. But we also have some pebbles that are less than 0.5, which are likely segments that don't represent true pebbles. For example, this is a boulder that is covered by a second boulder, and the normalized isoperimetric ratio here of this boulder is lower because we don't know how it continues below that cover. So let's pick out the isoperimetric ratio pebbles less than 0.6. I'm using 0.6 as a threshold, but you can use 0.5 or any other threshold that you would like or that you deem to be useful for your environment. If you expect that you only have very well-rounded pebbles, you may actually set this higher to 0.7. So we now see the list of pebbles that are less than 0.6, that are less round than the factor 0.6, and we would like to also visualize this. So we can create a new label data set that only contains the labels with a roundness that is less than 0.6. So we are doing that to essentially verify if it's safe to remove those labels. And what I'm plotting here is the original mask data set in grayscales, and all colored pebbles are the ones that have an isoperimetric, a normalized isoperimetric ratio less than 0.6. And you can see that, for example, this guy here that is partly covered, as well as other pebbles that are partly covered by pebbles, they tend to have an isoperimetric ratio that is fairly low. So that would be safe to remove those pebbles and then plot the size distribution of the remaining pebbles. So that is a simple but very efficient filtering step that also allows you to digest larger data sets. I hope you find this video useful, and thank you for listening.